Hey! Hope everyone is having a good week. Today, as promised, we'll be continuing our discussion on action potentials. Okay. So in the last discussion, I didn't define what resting membrane potential means. It is defined as the transmembrane potential that exists in a cell when the cell is not being excited. So we have a few new terms here. Transmembrane potential. Transmembrane potential means membrane potential that exists across the membrane. Okay, that is what is called a transmembrane potential. Okay, and when the cell is not being excited, what does the word excited means? Okay, or what are excitable cells? Excitable cells are those cells that have the ability to produce action potentials. And today we'll be discussing on the same. Okay, and you will get a clear-cut idea of what all this definition really meant. Okay, so in the last session, if you recall, we had a cell here. Okay, and the cell always had a pump here that had the ability to pump 3 sodium out for every 2 potassium taken in. And what was that pump? Yes, that was the sodium potassium ATPase. And it always pumped 3 sodium out for every 2 potassium taken in. Okay. We also had some leaky potassium channels. For all the new ones who are watching this video for the first time, just watch my previous video on membrane potentials so that you will be clear of what I am drawing here. So we had the leaky potassium channels, and also in that session I told you we have very few sodium leaky channels too. Okay, sodium leaky channels, but they don't contribute much towards our resting membrane potential. Okay, now what was the resting membrane potential? It was in the range -90 to -70 millivolt, right? So for our discussion sake, I will be taking it around -90 millivolts. Okay. So when you refer your text, you can see there is a graphical representation for this membrane potential and action potentials. So we will be seeing how it looks like. The ideal resting membrane potential that we learnt in our last discussion was, it was around -90 millivolt, or it falls in the range 90 to 70 millivolt, right? But since nothing is ideal, and due to the presence of some or very few sodium leaky channels, that leads to the efflux of sodium from the cell, not all cells can attain the resting membrane potential of -90 millivolt, which is the equilibrium potential or Nernst potential for potassium. So when potassium escapes, or when there is potassium efflux from the cell tries to achieve the equilibrium potential for potassium, which is around -90 millivolt. But due to the fact that conditions are not ideal and there are a few sodium leaky channels which promote the leaking of a little bit of sodium out from the cell, this resting membrane potential varies from -90 to -85 millivolt, or it climbs up to 85 millivolt, which becomes the resting membrane potential under practical conditions. So we have 2 bars here, one showing the ideal resting membrane potential for a cell, and the second one the membrane potential that is existing practically in all the cells. So we have the 99 and 85 mark. Okay, so now let us see a few new terms. One is threshold potential. Okay, what is threshold potential and what happens when threshold potential is achieved. These cells, as you can see, apart from the leaky potassium channel, the sodium potassium ATPase and the leaky sodium channels, we have some other channels or some other proteins called the voltage gated sodium channels. Voltage gated sodium channels. And how do they look like? They look like a cylinder and they have two gates. Okay, and what are those two gates? One is the activation gate and one is the inactivation gate. Okay, or simply this is the M gate and this is the H gate. Okay, M is the activation gate, H is the inactivation gate. When a cell's potential climbs from -85 to the threshold potential, that is around -60 millivolt. Okay, when it climbs up to the -60 millivolt mark, which is called the threshold potential, these voltage gated sodium channels, as the name suggests, they are dependent on a particular voltage. Okay, these channels starts to open, that is their activation gate starts to open slowly and their inactivation gate starts to close at the same time. Okay, as these gates open, you know that outside the cell the concentration of sodium outside the cell is too high, right? So when the voltage gated sodium channel starts to open, it sees an opportunity to get into the cell, and all this sodium that are present outside the cell starts to get inside the cell. So there will be sodium influx. Okay, there will be sodium influx. And how long will this sodium influx continue? I told you in the last session, whenever an ion moves out of the cell or inside the cell, it always tries to achieve its equilibrium potential for that ion or Nernst potential for that ion. For potassium it was around -90 millivolt and for sodium it is around the +65 millivolt. So as soon as a cell achieves the threshold potential of -60 millivolt, the sodium channels which had their activation gates closed and inactivation gate open, initially which was in this state, it starts to open and it causes the influx of sodium, because now sodium sees a way into the cell. There will be a rapid influx of sodium into the cell and this sodium will try to achieve its equilibrium potential of +65 millivolt, and thus the graph climbs to from -60 to around towards the +65 millivolt mark. But the sad thing, before the potential reaches before the potential of the cell reaches 65 millivolt, the inactivation gate for sodium voltage gated sodium channels closes, and thus there is no more influx of sodium. Sad ending to the story. And thus sodium does not achieve its equilibrium potential. But currently the potential of the cell is nearly positive. Right. Now, what happens? Apart from this voltage gated sodium channels, there are also voltage gated potassium channels. Okay, and this voltage gated potassium channels are activated at the same time when these voltage gated sodium channels are activated. That is when a cell achieves the threshold potential. So, what does voltage gated potassium channels do? They allow excess of potassium to move out of the cell. Okay, and how long will this process continue? Till it achieves the equilibrium potential for potassium, that is around -90 millivolt. So same time both the channels are open, but the sodium influx is too high when compared to the efflux of potassium. Okay, so the potential of the cell climbs nearly up to 65 millivolt, and after the closure of the voltage gated sodium channels, this voltage gated potassium channels still operate, and they are too sluggish, means they are too slow to close. They won't close at the same time this voltage gated sodium channels are closed. So they take their time to close, and during that time period, a lot of potassium is now pushed out of the cell. Okay, lot of potassium is pushed out of the cell, and now what happens? Potassium efflux is continuing till it achieves the equilibrium potential for potassium, and thus this potential, this is the potential of the cell, which was earlier near to the 65 millivolt mark, starts to drop, and it drops, and it reaches eventually the negative 90 millivolt. Okay, and after that voltage gated potassium channels close. Okay, so in summary, we had a normal cell which was having its normal membrane potential, and for some cause the resting membrane potential of negative 85 millivolt reaches the negative 60 millivolt mark. And when the cell potential of the cell reaches from negative 85 to negative 60 millivolt, that is the threshold potential, the voltage gated sodium channels as well as the voltage gated potassium channels both open. Okay, and the voltage gated sodium channels, which are initially in this format, the activation gate is closed, the inactivation gate is open. But when the cell reaches the threshold potential, the activation gate starts to open slightly, and the inactivation gate starts to close. Okay, and when this happens, or when the gate is in the second phase, there is a rapid influx of sodium into the cell. At the same time, there is a efflux of potassium too, but the influx of sodium is far greater than the amount of potassium that is moving out. Okay, with the help of both voltage gated and leaky potassium channels, and the sodium influx continues till it reaches the equilibrium potential for sodium, and thus the potential of the cell starts to climb, and before it reaches 65 millivolt, the so voltage gated sodium channel closes, or the inactivation gate of the sodium channel closes, and thus there is no more influx of sodium, but the voltage gated potassium channels continues its work. It continues to push out potassium through its channel. Okay, and since it is slow to close, the potassium efflux will continue till the potential of the cell reaches around negative 90 millivolt. Okay, and when this closes, everything is back to normal again. There is no voltage gated sodium channel open, there is no voltage gated potassium channel open, there are only the sodium potassium ATPase left, and the leaky potassium channels in working. So this potential then eventually climbs up to our negative 85 millivolt mark. So now we have a graph here, right? This graph which we have drawn now is the graph of our dearest action potential. Okay, so everything that happens in the cell, or the electrochemical changes that happens in the cell after the cell achieves its threshold potential, is referred to as our action potential. Okay, but now, do every cell have this ability of creating an action potential? Okay, or do every cell have the ability to reach this threshold potential, after which only the action potential is created? The answer is no. Not all cells can produce action potentials, and as told earlier, all the cells that can produce an action potential are referred to as the excitable cells. Okay, and who all are these excitable cells? We have the neurons, or our nerve cells, which we are currently discussing on, and then our muscle cells. And these muscle cells can be our skeletal muscle, smooth muscle, or cardiac muscle. Okay, so the neurons and the muscular cells, or the muscle cells, are the excitable cells, and they are the only one that have the ability to attain a threshold potential, after which an action potential can be produced. Okay, now we will see how a cell reaches the threshold potential from its resting membrane potential. Okay, consider this to be my fingertip. Okay, I have my nail here. This to be my fingertip. Okay, someone gives me the slightest of touches. Okay, and what happens when someone touches me the most slightest way? There are touch sensitive mechanoreceptors over here. Okay, and this receptor is this one. I have zoomed this. Okay, this one is, this picture is, or this cell is zoomed. Okay, and this is our touch sensitive mechanoreceptor. Okay, when this touch sensitive mechanoreceptor is stimulated, depending upon the amplitude or depending upon the force of the touch, these mechanoreceptors allow sodium influx. So when it is the slightest of the touches, the amount of sodium that it allows inside the cell are very minimal. Okay, so showing this in the same graph, when it is the slightest of the touches, there is a bit of sodium influx, and the resting membrane potential from minus 85 millivolt moves to minus 83 millivolt. Okay, just a 2 millivolt difference. Okay, so it just rises a bit. Okay, and then when there is no touch again, it dies off. Okay, it dies off. Now someone touches me with much more force. Okay, this time of the touch is of a much more greater amplitude, and what happens? The mechanoreceptors are stimulated much more, and thus it allows much more sodium inside. Okay, so the minus 85 millivolt now moves to minus 80 millivolt. Okay, so it is of much bigger amplitude, but still it doesn't reach the threshold potential, it dies off. Okay, now someone touches me with enough force. Okay, enough force that the mechanoreceptors allow enough sodium influx to make the membrane potential from negative 85 millivolt to negative 60 millivolt. And when the membrane reaches the negative 60 millivolt, you know the rest of the story. What happens? An action potential is created. And how? When the membrane reaches the negative 60 millivolt, our voltage gated sodium channels and voltage gated potassium channels open. And the influx of sodium is much greater than the efflux of sodium provided by the leaky potassium channels and the voltage gated potassium channels. And thus, there is a rapid influx of sodium. Sodium tries to achieve its equilibrium potential, and before it could reach the equilibrium potential, the voltage gated sodium channels close, and still who is working? The voltage gated potassium channels and the leaky potassium channels are working, and it brings back the potential back to the equilibrium potential for potassium, and then after everything is closed, the cell becomes normal. Only the leaky potassium channels and sodium potassium ATPase is working, and a bit of our leaky sodium channels may also work, which contributes a bit, and the resting membrane potential moves to negative 85 millivolt. This is what happens, right? So I told you there were two examples. Okay, the first potential couldn't reach the threshold potential, the second potential couldn't reach the threshold potential. All these potentials which were enough to stimulate the touch sensitive mechanoreceptors, okay, or the mechanoreceptors, but couldn't reach the threshold potential, are called the sub-threshold. Sub-threshold means they couldn't reach, or below the threshold. Sub-threshold potentials. Okay, sub-threshold potentials can also be called the local potentials. Okay, these are also called the local potential. But when the local potential is of enough amplitude so that it can reach the membrane potential of negative 60 millivolt, then it is transformed into the action potential. Consider ourselves here. As told earlier, we have our sodium potassium ATPase that pumps 2 potassium in for every 3 sodium pumped out. We have our leaky potassium channels, okay, which permit the efflux of potassium from the cell. So as I told you earlier, the potassium concentration in the cell rises up due to the sodium potassium ATPase. And since the concentration of potassium is high inside the cell and it is low outside the cell, the potassium starts moving out. Okay. I also told you that inside the cell always electrical neutrality is maintained. So for every potassium available in the cell, there is always a negatively charged particle. Okay. But when this sodium leaky when this potassium leaky channels are open, this potassium starts to move out of the cell. Okay. And thus leaving behind the negatively charged particles or anions. Right. This was something we learned in the last class, right? Now, since this cell is now having a negative charge or an electronegativity inside, this state of the cell is called the polarized state. Okay, polarized state. When a cell reaches the threshold potential, what happened? There was rapid influx of sodium, right? And what happened in that? The cell's potential started to climb from negative 60 to positive 65 millivolt. Means the cell's potential is moving away from the baseline, right? Or the cell is being more and more positive, right? So the polarized state was the negativity, electronegativity present within the cell. Now when the cell is being more and more positive, what is happening? The negativity is being neutralized. Positivity is climbing. What is happening? The cell is becoming depolarized. Okay, the cell is becoming depolarized. And when it reaches close to 65 millivolt, the sodium channels, voltage in the sodium channels close. And now what is happening? The voltage gated potassium channels and the leaky potassium channels are both working to push out the potassium to regain the resting membrane potential, right? So the cell is trying to bring in electronegativity. So the potential drops from around this positive 60 millivolt to or 90 millivolt. And what is happening here? The potential is becoming back to its normal resting membrane potential. This is called, and since it is being achieved after being depolarized state, it is called repolarizing. Okay, repolarizing. So the cell is repolarizing itself. It reaches the negative 60, then it reaches negative 85. Now, the negative 85 was a normal resting membrane potential. But due to the action of our voltage gated potassium channels and our leaky potassium channels, the potential further goes below, or it goes more negative from negative 85 to negative 90. Means it is being more polarized. And this more polarized is termed as hyperpolarization. Okay. These are few terms that are something you are going to encounter in your textbooks. Okay, so the cell, when it gets enough stimulus, it reaches the threshold potential, and from the threshold potential, the cell is depolarized. From here, it is depolarized, and after the sodium voltage gates are closed, it starts to repolarize. And after repolarization, it reaches the normal resting membrane potential. But due to the action of our voltage gated potassium channels also, the cell's potential goes more negative or becomes more negative, and it reaches up to negative 90. This phase is called the hyperpolarized state. Okay. Okay, so now we are moving towards the end of our session. We will discuss a few more terms. Okay. So this is my finger. Okay. This is the finger zoomed. Okay. Here we have our touch sensitive mechanoreceptors. We have our voltage gated sodium channels. We have our voltage gated potassium channel. We have our sodium potassium ATPase, and we have our leaky potassium channels. Okay. Now consider our cell. Someone touched me. Okay. It is not only touch, it can be any stimulus. Okay, if the stimulus has an amplitude that can cause the cell to move from the resting membrane potential to the threshold potential. Okay, so here I am taking touch as an example. Someone touched me with enough force or enough amplitude so that my touch sensitive mechanoreceptors, which are sodium channels, they allowed for some sodium influx and my potential reached the threshold potential. Okay, you know the rest of the story. And from there, when it reaches the threshold potential, my voltage gated sodium channels open. They allow an influx of sodium. And there are also voltage gated potassium channels which cause the efflux of potassium too. But here the voltage influx of sodium is much greater. Influx of sodium is much greater than efflux of potassium, and thus the potential climbs in a target to achieve positive 65 millivolt. But before it can achieve that, the voltage gated sodium channels close, and since the voltage gated potassium channels are still in action, and since potassium is lost from the cell, the cell starts to reach its resting membrane potential or the equilibrium potential for potassium, and it then drops and then it becomes normal again. This is what we learn from our action potential graph. Right. Now, there is something more interesting that happens too. When the cell reaches a threshold potential, there is a large influx of sodium. Right. There is a lot of influx of sodium from outside the cell to inside the cell. Okay. And some sodium moves to the nearby area too. Okay. Some sodium moves to the nearby area also. This is one part of the area. See, this is one part of the area. And this is what is I'm showing. Okay. And when there is sodium influx, and when sodium occurs, when sodium influx happens, some sodium moves to the nearby cell also. Okay, the nearby cell also, and this sodium causes the nearby cell's resting membrane potential to climb from negative 85 to negative 60 millivolt. Okay, and an action potential is also created in the nearby cell, and this process continues. Okay, this process continues till the information reaches our brain. Okay, so what can you understand? Once an area is depolarized, the depolarization wave spreads across the membrane of the cell like a ripple, right? So, and this way the electrical signal reaches our brain, and that is how we perceive it. Just because an impulse was produced here doesn't imply that I can perceive that, right? This sensation which I felt here should reach my brain, and then only I'll be able to perceive, okay, someone has touched me or something has hurt me, right? So that particular sensation reaches the brain in this format. Once one small area of the cell is depolarized, the nearby cells are also depolarized due to the influx of potassium that happens, or influx of sodium that happens, and thus this depolarization wave spreads like a ripple till the information reaches our brain, and our brain processes it. Okay, so what did you understand? These action potentials that are produced move, right? Or they are able to propagate. So action potentials are sudden and rapid electrochemical changes produced over the membranes of the cells that have the ability to propagate. Okay, and action potentials can only be produced by excitable cells, and these excitable cells are our neurons and muscular cells. They only have the ability to reach from our resting membrane potential to the threshold potential and then produce the action potential. Okay, so this was one thing. The other thing, consider someone touching me with the slightest of the touch. I have my potential and it dies off. Okay, but imagine a situation where someone is touching me repeatedly like this. Okay, so there is a potential, and before it dies off, there is another touch, and thus there is another touch. Okay, still it didn't reach the threshold potential, but then before this potential dies off, there is another touch. So what is happening? The local potentials are adding up till it reaches the threshold potential, right? So these local potentials can be summed up, or they can be added up to reach the threshold potential if I give the enough repetitive potentials, right? So this is called the law of summation, right? So our local potentials or the sub-threshold potentials can sum up or add up to reach the threshold potential, right? Now I told you, when the touch is slightest, I have a slight potential, right? When the touch is too much force or too much amplitude, the potential eventually hits the threshold potential, right? So the way I touch or the amplitude of my touch, the produced potential or the produced local potential is dependent upon the amplitude of the stimulus. It is referred to as graded potential. Okay, graded potential. Graded potential means something that depends upon the amplitude of the stimulus. So since these local potentials are dependent on the amplitude of the stimulus, they are referred to as graded potential. Let us see a few differences between action potentials and local potentials. Okay, local potentials are graded potentials, right? They depend upon the strength of the stimulus, but action potential doesn't depend upon the strength of the stimulus. Means once the threshold is achieved, okay, an action potential is created. It doesn't depend upon the strength of the stimulus. If the stimulus is too strong, faster it reaches the threshold potential. But after that, it doesn't depend upon the strength of the stimulus. If the strength of the stimulus is too low, it takes time to reach the threshold potential. That is the difference. So action potentials are independent of the strength of the stimulus. Okay, 1. 2. Action potentials have the ability to propagate, right? That's what we discussed. Action potentials can move across the cell, whereas local potentials cannot. Okay, so, and third one, local potentials follow the rule of summation. See, I told you earlier, right? If there is repetitive stimulus, and if these repetitive stimulus are acting in a short period of time before the earlier potential dies off, it can sum up to reach the threshold potential. Okay, so 3 points. One is local potentials are graded potentials. They follow the rule of summation. They are non-propagative. Okay, and action potentials, they are non-graded potentials. They doesn't depend upon the strength of the stimulus. Second one, they are stereotypical. Okay, I'll tell you what it is. They are stereotypical. And third one, they do not follow the rule of summation. Okay, so what is stereotypical? A particular type of cell, when stimulated n number of times, okay, it produces the same pattern of action potential. So if I have a nerve cell, okay, I have my neurons, this is my nerve cell, and when I stimulate this for the first time, I will have the same action potential graph. Okay, when I stimulate it after 10 minutes, I will have the same action potential graph. If I stimulate it with a much greater force, still I will have the same action potential graph. Okay, means the type of cell, action potential graph is dependent on the type of cell. It is independent of the time, it is independent of the strength of the stimulus. Okay, so if the cell is the same, the type of action potentials we receive are identical. So if I have two nerve cells, say A and B, stimulate them both enough to reach the threshold potential, I will have both the action potential graph being identical to each other. But if I stimulate a nerve cell and a muscle cell, okay, then there might be a change in the action potential graph. The nerve cell action potential might be in this way, the action potential might be a bit smaller. Okay, and that totally depends upon the amount of sodium present outside the cell, amount of potassium present inside the cell, the resting membrane potential of the cell. Not every cells have the same resting membrane potential. I told you it is around the range of -90 to -70. So from it can vary in this range. Okay, so different excitable cells means different action potential graph. The same cell means the identical action potential graph. So that identical action potential graph that we get due to the same cell when stimulated in whatever way we can is referred to as stereotypical. Okay, so this is the end of this action potential topic. Okay, I hope you have understood the generation of action potential, how it moves through a cell, what the terms depolarization, hyperpolarization, polarization means, and what are the differences between action potential and local potentials. What are local potentials? I think I have answered all these questions. Okay, so I hope everything made sense now and everything is clear. See you in the next session, and if this proves to be of any help, please to show your support by subscribing to my channel and do like this video too. And that's it. Have a nice day. Bye.